probability that one event happens and that given that pretty important, given that another event is known to happen. Show you how the notation works. The conditional probability is the probability that one event happens given that another thing is known to already have happened. So let's say we know A is happening. Doesn't matter what A is. And you don't have to write this if you don't want to, but let's say we know A has happened. The probability that B happens given that A has already happened, how would you write that with our notation? Okay, you would say, what is the probability, big P, open your parentheses, what's the probability of B, given that, you know the given that symbol? Straight line, A has already happened. The second thing, the thing right here, is the thing that's already happened. The first letter, or whatever that is what we're trying to find out. So, what's the probability that we get sick, given that we were around someone that was sick? But whatever is here already happened, and that's the only one we're looking at. So let's just kind of work this down so we can find it. Before we work on this table about allergies and no allergies, let's get some totals. 18, 22, we're going to have 40. Is there a relationship between gender and having allergies? And you can't common sense these, like you can't, there's no way to tell until you crunch the numbers. You can't say, oh, that doesn't make sense or whatever. There's not really an intuitive way to do this. You just gotta crunch the numbers. To find out, we used the random sampler, the census at school website, and randomly selected 40 students. And there's our two-way table. So we randomly pull a student out of this sample and we consider the events. We're going to call A, they have allergies, and F, they have this is a female. So to find the probability that the student has allergies, okay, we have not narrowed our sample size down. We're just reaching in. So we're looking at 40 kids. Out of those 40, what's the probability that they have allergies? Awesome. And this is also called a marginal. Okay, so the probability that they're simply a female, haven't narrowed anything down, so we're looking at all 40. And let's see, yeah, 23 also. Okay, so this you're probably familiar with, probably been doing that for a while. This is where we got a little bit of notation, but it's not difficult at all, I promise. You read this as the probability of having allergies given that you're a female. Okay, this is going to give you your denominator because that's the condition. We're only looking at females. You can even pretend the males are not there. So for the probability that you have allergies given that being a female has already occurred, remember the definition. Awesome. All this conditional thing does is limit your sample size, basically. Because before we were looking at everybody, now we're just looking at whatever that condition is. And look, it's going to be different, the probability of female, given that you already have allergies has occurred. Now the condition is allergies, and we're only looking at folks with allergies. And we already know 18. Yep. So that's really all there is to conditions. It's a condition that's already occurred, and that kind of limits your sample space, and you just kind of go from there. Okay, I'm going to tell you, for this one, on the test, you're going to have to prove this using a little bit of a formula, but it's not difficult, but I'm going to tell you in words first. How can you tell if two events are independent? If the occurrence of one event has no effect on the chance the other will happen. And very rarely can we tell just by looking. Like the thing with allergies and gender, you can't tell just by looking. The simple ones that we made up about turning left and right at the intersection or rolling a dice and flipping a coin, yeah, we can tell. Otherwise, you're going to have to use a formula. So if one event has no effect on the chance the other occurs, it's independent. Mathematically, here's how you show this. You would say that the probability of A happening is exactly the same as the probability of A happening given that B has already occurred. Now, that should make sense to you at this point, because if B has no effect on A, then that means they're independent. So mathematically, this is how you prove it. And you could flip it around. Maybe you want to say the probability of B is equal to the probability of B given A. See, B is not going to change whether A happens or not. That would show independence. If those are not equal, they're not independent. And it doesn't matter if you write it on the left or the right, but Are the events A and F independent, and explain? So are having allergies and being female independent of each other? Well, let's test it. If it's true, then the probability of having allergies is going to be exactly the same as the probability of having allergies given that you're a female. Well, we already know the probability of having allergies given you're a female is 10 over 23. And the probability of plain no allergies is 18 over 40. When we reduce, do we get the same number? Over here, we're going to get 9 over 20.
Would that be your explanation, like that word?
Yeah. This would be your explanation right here.
So you don't have to put any words other than yes or no?
Mm-mm. So are the events independent? No. And then show your work. You're done. You would need to do the yes or no, but other than that, that would be your work. And maybe you wanted to show it the other way. It would be perfectly acceptable to go the other route and say, okay, the probability of being female that you have allergies, is that the same as the probability of being female? If you had went that route, that would have been the same difference.
So your explanation is just your word?
Yep.
Okay, I'm just checking all of these.
I was just saying, you could have done allergies given female or females given allergies. Either way would have shown, and that it wasn't. Okay. Now, what is the general multiplication rule? Well, that's the one we put on our paper that's kind of on your reference sheet, but not general multiplication. Remember, we're thinking and here and multiply is the probability of A times the probability of B given that A has already happened. That's when you don't, when your events are not independent. Now, this is a special case, and we talked about it earlier. This is a special case. If they are independent, it's a little bit easier because it's just the probability of A times the probability of B. Now, we've talked about two very different things, mutually exclusive and independence. Mutually exclusive, we talk about that in context with your or. Okay? Mutually exclusive, you talk about it in context with your or. If they're mutually exclusive, you can kind of take it off this minus part. Independence, you talk about in context with your and statement. And if they're independent, it makes your formula a little bit easier. You can use the special case. So let me give you a second to read about tree diagrams. If you want to read over this, and then we'll put together a tree diagram. So a tree diagram is really useful to help you organize your thoughts. So you're going to start out with very basic, who are we talking about? Everybody okay? We start out with students. Okay, and the first thing they said about the students was light, moderate, and heavy media users. So we've got light, moderate, and heavy. And then along your branches, you need to put the probabilities. And I want to stop and see if that's okay. And I'm just reading through the paragraph, kind of putting in a tree what the paragraph told me first. This first thing it told me. We got students. They're divided into three distinct groups. Now, they break it up even further. If you're a light user, 74% said their grades were good. And then that means, by definition, 26 would be bad. So far, so good about how I'm filling this out. Okay, and the moderates, let's see, 68 had good grades. Yeah, so that's like good. 32% for the bad. And then for the heavy, 52% said their grades were good. And 48. And you will probably have to make a tree diagram. That will be one that I give to you and ask you to interpret. Any questions on the tree diagram before I move on?
Please refer to test.
Do what?
Quiz or quiz?
I don't know, either way. It's one of those where you probably have to make this yourself instead of interpret. Usually the two-way tables are good for you, but a lot of times if I give you this information, you're going to have to put it in a table. It's not good for you as long as you keep up with it. The question finally asks, according to this study, who described their grades as good? So what's our probability statement going to look like? Probability of described grades as good. Or you can identify a subscript somewhere else and use that, or you can just write that in there. But you gotta have this probability statement right here. That's gotta happen. Okay, so let me show you how to get this good business. If you look at your last branch, do you see where the three goods are at? Okay, so we want something here, we want something here, and we want something here. What do you think we need to do with these two numbers? We've got a .17 and a .74. What do you think we need to do with the number to get what number goes here?
Take the percentage, or take 0.74 out of it. I don't know if I'm describing it well. What is 0.74 and 0.17?
All you really have to do to get this good is multiply, because we want light and good. And remember, and, we're thinking multiply, so light and good, all you have to do is multiply, and let me crunch that number for you, so you have to, it's 1258. Here, the way we got to good was moderate and good, and we're thinking multiply, so that's 0.4216. And then heavy and good, so we're thinking multiply. So we got our three numbers. And what you're going to learn is when you go across the branches, you multiply. When you go down the tree, you add. And that's not a real mathy thing, but it does help you when you're going across these branches, you multiply. When you go down, you add. Because to actually get the probability that your grades are good, you could have done this. What's the word you would put between this? You could have done this, or you could have done this, or you could have done this. And what math symbol do we always associate with or? Plus. And is multiply, or is add. So if you add all three of those together, and I want to come out to the side just in case you look back up here and you look back at your notes. Add 0.6566. Is there anything I can clarify at this point, or are we okay? Might need some practice where you have some questions. Okay. What is the multiplication rule for independent events? We've talked about it a couple times. It's simply the probability of A times the probability of B. Very simple if they're independent. How is it related to the general multiplication rule? Well, you just don't have to take into account the effect A has on B, because we're saying they're independent. It doesn't have any effect. What is the difference between mutually exclusive and independent? Okay, you're going to need to think about mutually exclusive when you're looking at the or, there's the symbol. That's when you're going to have to think about whether it's mutually exclusive. And it means simply can't happen together. And however you want to think about mutually exclusive, it's hard to come up with a great example because there's an exception to everything. In the book, I think it says if A, the person is male, and B, the person is pregnant, we're thinking about that being mutually exclusive. But two things that can't happen together are mutually exclusive, and you've got to take that into account with that formula. Okay? Independent, you want to think about whether it's independent when you're looking at and statements. And it just means, you ask yourself a question. If you know A has happened, does it affect B? And a good example of independence is if you flip a coin and roll a dice, whether you get heads or tails has no effect on what number you get on your dice. And we looked at how to mathematically prove that. And let me give you just a statement, and we'll talk about why it's true, and then I'll let you work on your homework. And then tomorrow at the beginning of class, I'll answer questions to both nights' homework. And I put the night before's out to the side. So we've got Thursday night's homework there to the left, and this night. Tomorrow we'll kind of go over both. So let me give you this statement, because this comes up on the exam all the time. Two mutually exclusive events can never be independent. And intuitively, that's hard to wrap your mind around because you're thinking, okay, mutually exclusive means they're independent. But if they're mutually exclusive, they will never be independent. And let's think about why. Mutually exclusive events means if A happens, B will never happen. They can't happen. How does that mean they're not independent?
Because it can also mean if an event is dependent on the other event, that if one happens, then the other can't. That's a type of dependency.
Absolutely, because we're not saying what kind of effect, but it will have an effect. Because if we know A happens, B will never happen. That's an effect. So that's just a good, that it's asked in multiple choice questions in a variety of ways, but just make sure you have that. And let me give you the last 15 minutes to work on your homework and get some of that knocked out. And then tomorrow we'll go over both. I don't know. I'm sorry. I'm terrible.
You guys want me to read it out loud to you? Because I can read it.